Good morning. Welcome to our presentation. Our topic is HiPa, Hierarchical Partitioning for Faster PageRank on NUMA Multicore Systems. Our talk consists of 4 parts. In the introduction, we will give the background information and the motivation regarding our work. Then, the design of HiPa is discussed in details in the second part, and its performance is evaluated in the third part. Finally, we conclude our presentation in the last part. Firstly, let's briefly talk about the PageRank algorithm and the computation issue it faces. PageRank is one of the most basic graph algorithms. It was proposed to measure the importance of web pages on the internet. The larger the rank value, the more important the page. PageRank is proposed by Larry Page, who is the founder of the Google. Thus, PageRank can be considered as the ancestor of Google's search engine. Also, there are many people arguing if the word page here means the name of Larry Page or web page. Here, we present the formula of PageRank. In short, it is an algorithm that iteratively performs multiplication and addition of metrics. During each iteration, all vertices and edges are engaged in the computation. Normally, it takes around 50 iterations for the algorithm to converge. And please notice that the number of edges is usually significantly larger than that of vertices. As a result, the workload of PageRank mainly depends on the edges of the graphs. The computation of PageRank, as well as many other graph algorithms, suffers from the random access of graph components. This is because graph is a point-based data structure. Such structure poses considerable negative impact on the data access pattern. Here, a random graph is illustrated. Its elements are sparsely distributed in the adjacency matrix. So when goes through the graphs along the edges, the access to the data is highly irregular. Another important issue that slows down the performance of graph processing is the skewed power law distribution. In such case, a few vertices are responsible for a majority of connections. Many natural graphs connected from a real world show such property. The skewed degree distribution causes extremely imbalanced workload for parallel graph processing and thus slows the speed down. To cope with those issues, we propose HiPa, which splits the graph at both memory and cache level. The conceptual design of HiPa is illustrated here. It exploits the NUMA architecture of memory system and the private cache of each processor core. A graph is firstly partitioned according to the NUMA node and then according to the L2 cache. At the memory level, our goal is to place the computation and the data as close as possible. The first step follows our intuition that each NUMA node is allocated with the same number of edges to balance the workload. In the second step, we make a slight modification on the result of the first step. The vertices assigned to each NUMA node must be multiple of L2 cache-sized subgraphs. The number of partitions is the least succeeding integer of Vi divided by P. Accordingly, the edge subsets are resized. In the third step, we focus on improving the cache locality. The cache-level subgraphs are organized into several groups. Each group is allocated to one specific processor core. Those groups contain roughly the same number of edges for workload balance. A partition is the smallest data unit as the input for each thread to process. The cache enable disjoint partition limits the data access within L2 caches for high cache locality. Here, we only use the L2 cache as an example for explaining the partitioning strategy of HiPa. In later section, we will describe how do we obtain the optimal partition size. Here is the partitioning result of HiPa. At the first level of memory, the graph is partitioned into 2 segments, and then at the second level of private cache, the graph segments are further divided and grouped. These groups are assigned to individual processor cores with unique ownership. The final result is that the cores are allocated with unequal number of partitions but equal number of edges. The programming model of HiPa is presented here. To place the data and the computation together, the threads must be bound to specific NUMA nodes as well. Hence, the binding threads result in thread migration, which is highly time-consuming. To reduce the cost of thread migration, we enhance the functionality of threads. The scatter and gather phrases are included in the thread, and each thread covers the complete computing procedure of PageRank. Now, let's evaluate into the performance of HiPa. The experiments are performed on a multi-core system with 2 NUMA nodes. Each NUMA node has 20 threads with 1 megabyte L2 cache. HiPa is compared with 2 hand-optimized codes as well as 2 framework-based implementations. We firstly compare the execution time of HiPa with other implementations on 7 large graphs. HiPa achieves the lowest execution time on the majority of graphs. The hand-code implementations provide better performance than the framework-based implementations due to lightweight designs. In this slide, we show the memory access of the PageRank. The total bar is the summation of remote and local memory access. The lower shadowed bar is the remote memory access. As we can observe, HiPa causes the least number of remote memory access, even though it introduces slightly more total memory than the hand-code implementations. The reduction in remote memory access is the essential reason for the speed up of HiPa. Another advantage of HiPa is the scalability. Conventional partition-centric implementations achieve the best performance at about 20 threads. However, as the number of threads continues to increase, their performance begins to decline because of the growing contention on memory buses and private cache. By contrast, HiPa achieves the best results with 40 threads utilized. This is because HiPa effectively reduces the thread contention on the hardware resources by allocating data to specific threads. Lastly, we conducted the sensitivity analysis relating to the partition size. Experimental results show that the best performance of HiPa is achieved when the partition size is a quarter of L2 cache on Intel Skylake processors and a half of L2 cache size on Haswell processor. If the partition size is larger than the threshold, a large number of data processing will be split over onto the last level cache, thus decelerating the overall performance. To wrap up, HiPa applies 2-level partitioning strategies on the graphs. Firstly, the graph is partitioned according to the NUMA memory architecture. Edges for each NUMA node are balanced. Then at the second level, the graph data are partitioned again to feed into the private cache of process cores. The partitions are pinned to the cores to place the computation and the data as close as possible. In addition, the data layout are optimized for efficient memory access. More details relating to those technical optimizations can be found in our paper. The performance boost of HiPa can be found in several aspects. It speeds up the processing time. It reduces the remote memory access and ensure high scalability. And that's all for our presentation. And thanks for your listening.